Today's class, we will see silent features of Mendeleev Periodic Table. So as you know, Mendeleev proposed this table in the year 1869. He had only 63 elements and he classified them into a table. What you see on the board, I have given a sketch of modern periodic table designed by Mosley, and this is according to atomic number. Drawing a periodic table is also very easy. See, I have drawn 18 columns. I have drawn 18 columns and 7 horizontal rows. 7 horizontal rows. These are horizontal rows and 18 columns like this. Right? So what we need to do is very simple. First period, this way we call it as period. This way we call it as period. And down the track we call it as group. Therefore, this is first period. This is second period, this is third, this is fourth, this is fifth, this is sixth, and this is seventh. So I am speaking about modern periodic table because I want to give a clear-cut idea between these two. And you know very well, right? Mendeleev Periodic Table is considered great of the greatest. Okay, and today's table what we are following is Mosley's, designed by Mosley, atomic number. It's based on atomic number. While Mendeleev periodic table is based on atomic weight, but still till day you don't find much difference between Mendeleev periodic table and Mosley. So very important is Mendeleev periodic table. And Mr. Mendeleev was also called as father of periodic table because he has arranged those elements which were available at that time, 63, in a definite pattern. And till day, you don't find much difference in that pattern. Only the design changed. The design changed because of the electronic configuration. Because Mendeleev was following atomic weight. Today's periodic table is based on atomic number. So it is designed according to molar chart. That's electronic configuration. But the periodic table that was designed by Mendeleev, which was based on atomic weight, is quite different. Now we'll see. Now I am speaking of modern periodic table on the board because I want to compare these two. So I require a modern periodic table. And let me tell you, drawing a modern periodic table is very easy actually. Right? You have to draw 18 columns like this, 18 columns. And horizontal rows, 7 horizontal rows. These are called periods. So periods are generally period. They are represented like this. And down the track, if you go down, then it is called as group. Right? It is called as group. So it's understood there. Let me remove. So first period has got only 2 elements. So all this should be rubbed. So let me rub off what is not required. First period has got only 2 elements. Done. Second period has got 8 elements. Third also has got 8. So 1, 2, 3, 4, 5 and 6 up to here it is 6 over here. So 1, 2, 3, 4, 5, 6. Yes. This is your modern periodic table. See, such a easy thing it is. Right? Right now let me show you once again what is left over. So this is like this. Yes, this is your modern periodic table. Now, what happens in a modern periodic table? You have 7 periods. So, this way we call it as period. And you will have 2 more here, but they are continuation of 6 and 7. 6 and 7, you have a continuation. Meanwhile, groups, when you speak about groups, okay? When you speak about groups, there are how many groups? Group in the sense what? Speaking from top to bottom, we call them as group. How many groups do you think? This periodic table has, it has 16 groups, right? Let me point out those groups. This is first A group, this is first A, this is second A, here you come across here, this is third A, this is fourth A, this is fifth A, sixth A, 7 A, and this is inert gas, 0 group elements, noble gases, stable gases, all that. But anyhow, they come under 8th A also. They can also be represented as 8th A. Meanwhile, this is first B, this is second B, this is third B, this is fourth B, fifth B, sixth B, 7B, and these three put together it is 8B or 8. We call it as 8 or 8B. So altogether how many periods do you have? 7. These are called periods. Altogether how many groups do you have? 16 groups. So this is about modern periodic table. But people nowadays are having doubt, isn't it? There are 18 columns, but we are calling them by 16. So recently IUPAC, International Union for Pure and Applied Chemistry, is an organization which maintains all this throughout the world, chemistry throughout the world. IUPAC. Recently it has given numbering like this. It's 1 over here, this is 2, then this is 3, 4 over here, 5, 6, 7, 8, 9, 10, 11 and 12. This is 13, 14, 15, 16, 17 and this is 18. Done. You have 18 vertical columns. But still, you check it out here. These three columns, okay, these three columns put together, only one name is given. Why? Because all these have similar characteristic. If you place them over here, all these three, if you place them here down the track, design does not look good. That is why they are given three columns, and all the elements which are in these three columns, they have same characteristic. That's why they are designed into 8B. Right, now let us speak about Mendeleev Periodic Table. Mendeleev Periodic Table had a simple design, simple design. It was like this. Simple design, it's like this. Yeah, it went on like this, simple one. Right? What happens here? This is first and it is classified into A and B. So it's like this. This is second group and subgroups are A and B. This is third one, group A and subgroup A and B. This is fourth one with group A and B. So it went on up to 8th. Mendeleev Periodic Table also had 8 groups and they were also subdivided into A and B. Right, now let us speak about Mendeleev Periodic Table only, because our topic is today is Mendeleev Periodic Table. Right, good, then look at the board. Silent features of Mendeleev Periodic Table is silent. They say LIENT means important features of Mendeleev Periodic Table. That's what it means. It's not silent, it is silent features, okay? And among them the first one is about periods. Mendeleev Periodic Table, so our topic today is Mendeleev, not the modern periodic table. Mendeleev Periodic Table consists of 7 periods. It had 7 periods. So remember, it is all based on atomic weight. Mendeleev, we are not speaking about Mosley, not this one. We are speaking about the old one. Just for comparison, this is kept. Mendeleev Periodic Table had 7 periods. And they were given Hindu-Arabic numbering 1 to 7. Today's modern periodic table also same it is 1 to 7 and Hindu-Arabic system. So great, isn't it? We are following the same Mendeleev which is designed in 1869. Very good. Second, Mendeleev Periodic Table had groups 1 to 8 and they were again reclassified into subgroups like A and B. What are we having today? Same 8. First day, second day, third day, fourth day, fifth day, sixth day, seventh day, 8th day. 8th day is finished. First B, second B, third B, fourth B, 5B, 6B, 7B and 8B. We are following the same. Isn't it? Right, very good. Now coming to, there are few things which you are supposed to know. The formula given for this is called first A group element. This is called first A. Yeah, it's written on the top. You can check it out. This is called first A. And he has given a formula for this first A, R2O. And for the second A, he has given a formula called RO. What do you mean by this? Let us treat the elements which are in this first A as R. So I will take sodium for example. I will take sodium. Now what is the atomic number of sodium? It is 11. So it is 2, 8, 1 is electronic configuration. So its valency is +1. So let me write down sodium, it is +1 valency. Right? Now if it reacts with oxygen, O means it's understood it is with oxygen. Right, okay. Number is how much? 8. So it is 2, 6. How many does it require to obtain stability? It requires 2 because 6 isn't it. So it requires 2 to make itself 8 stable configuration. Right, you crisscross. So Na is given that 2 and O gets 1. What did I tell you about Na? You should consider that all the elements which are in this as R. Therefore the formula is R2O. Exactly. Finish. This is over. Finish. It's explained. Now coming to RO. So all the elements which are in this one, you have to take them as R. Okay, done. R. Right. Take any element in this one. Let's take the one which is beside sodium, magnesium, because it's like this. Hydrogen, okay, lithium, sodium, right, potassium, rubidium, cesium and francium. Here beryllium, magnesium, calcium, strontium, barium and radium. So I took one beryllium, magnesium, I took magnesium, right, okay. Magnesium number is 12. Magnesium atomic number is 12. So it is 2, 8, 2. So its valence is 2 plus. Cation. Oxygen, just now I told you it is 2 minus. Always it will be the same because its number is 6. 2 and 2 gets cancelled, therefore it is MgO. This is what you mean by RO. So if a first A group element reacts with oxygen, where do you find oxygen? It's here. It is in 16th group. 16 if you can, and 8 is a number. 2, 6. Therefore its valence is -2. You know the valences? The valence of, right, I will write this one. Yes, the valence of the first A group is +1. The valence of second A is +2. The valence of third A is +3. And the valence of fourth A is ±4. Then here it is, valence of 15 is -3. Then comes -2, -1 and 0. This is our valency. Right? It first increases, then it is decreasing according to the group. So I took this one, I took oxygen. So it is in -2 with valency. That's why we got the formulas R2O for first A group elements and RO for second A. Anyhow, I finished up to second point of Mendeleev Periodic Table. So the first point says that it has Mendeleev, not this one. This is modern. Mendeleev Periodic Table is such a simple one. I told you, it is just like this. It's just like this. That's all. So if you take a group over here and if you take another group, right, they are again reclassified into A and B. A and B. Yes, very good. A and B. This is also classified into A and B, but in a different way. Now we will see why it is. It is because of I told you electronic configuration. Now Mendeleev only will discuss. The third one. What is the third one? Excellent one it is. Third one is a very interesting point. See, Mr. Mendeleev, right? When he was designing the periodic table, there were only 63 elements. So he already designed it like this, okay? 8 elements, I said no? 8 columns. One, first A, second A, third A, fourth A, fifth A, sixth A, seventh A, and eighth A. Each one is again classified into A and B, A, B, like that he classified. So while he was filling the elements, at few places he didn't find a perfect element. So what he did is he left space there. So what exactly I want to tell you is, while Mendeleev was filling his periodic table, say like this, okay? Suppose I am taking only 2, no problem. Suppose I am taking, so this one is A and this is B. This is A and this is B subgroup. So while he was filling, right, say hydrogen he filled, and then he filled lithium, here he filled it, right? Next, what else? He is going on like that in his concept, okay? At one few places he left gap. He didn't fill any element. Because he predicted that new elements will be discovered and those elements will take this place, they will occupy this place. Who will think like that, tell me? That's why he is called father of periodic table. He left spaces in the periodic table. He didn't simply fill 63 like that, he didn't fill them. While he was filling, what he did, he predicted that here this is not the right element, some other element is supposed to come here. So in a course of time, one or the other will discover it or invent it, and that will be placed here. Therefore it is better I leave some space, like that he thought, and he left places. And he named that place, very interesting it is, he named it as Ekka. So I will fill the elements over here for some, right? He left the space and he called them as Ekka. So the first element here is hydrogen. This is modern periodic table. Helium, then comes lithium over here, beryllium, right? Then boron over here, carbon, nitrogen, as I already told you, oxygen, fluorine and neon. Now what else is here is sodium, right? Magnesium, then comes here aluminium, silicon, phosphorus, sulfur, chlorine and argon, right? Very good. So what happened, he left space here. This is one of the thing where he left space. He left space for the next one also here, right? What did he predict? He predicted that one or the other element will come here, because right now I don't have that suitable element, he thought, and he left space for the next element to come. And he also gave chance for the other scientists to think about element which is supposed to come here. These type of things are excellent actually, I can say. So, and course of, and how did he name, he gave the name as Ekka. These space items, they were called as Ekka. And he didn't leave it like that, Ekka. So this is aluminium, isn't it? Therefore, this was called as Ekka aluminium. This was called as Ekka aluminium. So he just selected top element and gave the same thing here, Ekka aluminium. This is called Ekka silicon, Ekka silicon. Because silicon is the element which is on the top of it, isn't it? And in course of time, this Ekka aluminium has become gallium. And Ekka silicon is germanium today. It is germanium, this one is germanium, and this is gallium today. Today's modern periodic table like that. Okay. And he also left space. Now, very interesting thing happens over here. Right? He left space here. And he left space here. Right? Ekka, this one, here. So what did he give the name here? Ekka boron. He called it Ekka boron. So you will get a doubt, isn't it? Where is boron and where is Ekka boron? Nothing else. This is, see, look at this one. This is third A, while this is fourth A. How did he classify? He classified in the same manner. No, A and B. So this is A boron. Next to third A, what comes? Fourth A. Third B. That's why Ekka boron is actually, it was just beside the A. Now in this periodic table, it is occupying this place. That is understood. But this is third B, and that is third A. So Ekka boron, course of time today, we know very well that it is scandium 21, atomic number 21. This is what Mendeleev followed. He left spaces in the periodic table. Right now, once again I am telling you, this is modern periodic table. His design was like this, so simple. 1, A and B, 2, A and B, 3, A and B, like that. Okay, done. And coming to the fourth important point is, he himself corrected the atomic weights of few elements. So that's what we call correction of atomic weight. Now, first he dealt with beryllium. We all know beryllium's atomic number is 4. So the configuration is 2, 2. So its valency is 2. But Mendeleev thought that its valency is 3. Therefore, he took the average atomic weight of the element. Average atomic weight means he is taking the weight of the next element and the element itself, and is dividing it by 2. So he found the average atomic weight of beryllium is 4.5, and he multiplied this with 3. Therefore, he got the answer as 13.5. But in the course of time, so right, once again I am telling you, Mendeleev periodic table is based on what? Atomic weight, right? So he gave more priority to chemical properties and physical properties. He didn't give priority to atomic weight also, but designed according to atomic weight. So when he got 13.5, so he wanted to arrange this element in the periodic table. His design like this, isn't it? Just now I told you, no, one means it is A and B. So he felt it is difficult, it is not coming to the right direction, is right point. Therefore, he thought, then he came to know that whatever the atomic, the valency he took, it was wrong. And finally, we know today the valency of beryllium is 2. So 4.5 into 2 is equal to 9, and we know its weight today is 9. So like that he corrected atomic weights. And how many elements did he correct atomic weight? He corrected atomic weight of 3 elements. So you can remember them as big, BiG. But let me tell you, it is not boron, but it is beryllium. Just now we have seen, isn't it? For our convenience, we can remember them as big, BiG. Now what does I indicate? Not iron, it is indium. So these are the sub letters, you can remember them. And this is nothing but gold, which is called as aurum. So he corrected atomic weights of beryllium, indium and gold. This is his fourth point, that is correction of atomic weight. Then comes the last and final, which is a very interesting I can say, anomalous series. Nobody I can challenge, nobody would have done this one. Nobody would have done this type of classification. That is why today, even though we have modern periodic table, still we call Mendeleev as the father of periodic table. Because I will speak about the last and final one, anomalous series. What does this mean? Super it is. Actually, Mendeleev periodic table is designed in this pattern. What is that? Increasing atomic weight. So what do you mean by this? So atomic weight increases from lithium to beryllium. What happens? Beryllium's atomic weight is greater than lithium. You mean to say boron, next carbon. So atomic weight is increasing. So ascending order he arranged. But what happens? Do you know? When you come across, see, fluorine, bromine, iodine here, and astatine, okay, this is work is going on, that's understood. And you will find here tellurium, because sulfur, selenium and tellurium. You know the interesting thing about these two? Like this, you will find 3 cases. The other one is with this one, okay, this neon and sodium. You will find this. What is that interesting thing, do you know? Tellurium's atomic weight is 127, while iodine's is 126. Actually, what tell me? Actually, it should be in ascending order, lesser to more. But what happened here? More is kept before less, right? More atomic weight is kept before less. Actually, it should be reverse way, but not possible. But he did not do that one. Why? Because iodine was having characteristics similar to fluorine, chlorine, bromine, right? Fluorine, chlorine and bromine. So he kept iodine here. Similarly, tellurium was having characteristics similar to oxygen, sulfur, selenium. Therefore, he kept it like that. And he called them peculiarly with a name called as anomalous. Anomalous series we call, and there are 3 elements like that, 3 sets like that, where more atomic weight element is kept before a lesser atomic weight, right? Thank you. This is all about Mendeleev periodic table.